Quicksort. We are going to learn also about the quicksort tree and the analysis of the quicksort. When we do the merge sort, it is based on the divide and conquer paradigm. So the divide and conquer paradigm is also used in the quicksort, but there is one keyword in the quicksort. We call it randomize. We use randomized sorting algorithm. So if you still remember, we use the divide, recur, and conquer on the merge sort, and it is the basis of the divide and conquer. Now in the quicksort, we are going to divide by picking a random element. In the merge sort, we will divide the element by 2. But in the quicksort, we will pick a random element, X, or we call it pivot. And we will partition S into L, which is the element less than X. And then E is the elements equal to X. And then G is the element greater than X. So if we choose X as the pivot, then we have E, which is the element equals to E, equal to X, and then L, which is element less than X, and then G is the element greater than X. And the same thing with the merge sort, we will sort based on this one. So we will check again which is another possible pivot, and we will do the recursion. At the end, of course, we will join or we will merge it. The partition here, if we use the merge sort, we will divide, so n power of 2. But the partition here, we will use a position P of the pivot. So we partition an input sequence as follows. We remove in turn its element Y from S, and we insert Y to L, E, and G, depending on the result of the comparison of the pivot. So let's say if I have P as the pivot, I prepare L, E, and G. Those are the empty sequence. And then X is from P. And then we want to check if S is not empty. So we will remove the first element and then check. If Y is less than X, then put them into L. If Y equals to X, then put it into E. Else means Y is greater than X, we put it into G. For every insertion and removal is at the beginning or at the end of the sequence. So it takes O one time. So this one is one time, or this one is one time. And the partition steps of the quicksort takes O(n) times, because this will be like O(n). So this is the implementation. The quicksort, the same idea with the merge sort. We will check the length, and then we have the base. The base case will be if n less than 2, then return. And then P will be the S dot first. So we have L, E, and G. So in this case, the authors use link Q. And we can check whether the S is empty or not. And then we will check this one. If S first is less than P, we will add into the L. If not, then we will add into the G. And if not, then it will be entered into E. And after we have L, E, and G, so we can do the quicksort with the L. This is the recursion. And after we finish with the L, which is the lower, we go to the next quicksort with the G. And then at the end, we can combine. So we combine it into S. If L is not empty, then first we add the L, because L is the left part. And then we add the E, and then we add G. We can also make a tree of this quicksort, similar to the merge sort tree, because we divide into two, which is L and G. The execution of the quicksort is depicted by a binary tree, and its node represent a recursive call of quicksort and stores unsorted sequence before the execution and its pivot, and sorted sequence at the end of execution. So first, maybe we can see the unsorted sequence, and then after we do the operation, we can get the sorted sequence. The root is the initial call. So this is the initial call. And the leaf are calls on the subsequences of size 0 or 1. So this is the leaf. When we do this quicksort, as we know, we need to select a pivot. The pivot selection is important. So let's say I have this number 7294371. Okay, I will choose this. So I need to make separation L, E, and G. So the 6 is the pivot. Then for every number less than 6, it will go to the left. And then again, I need to select another pivot. So every time I have a new element like this, I need to select another pivot. So this example, I use 2 for the pivot. Then if it is less than 2, we go to the left. If it is higher than 2, it goes to the right. Okay. So we call this is the L, or this is the G. In this case, we have the pivot is 3. Okay. Is there any number less than 3? We don't have it. So it is a leaf with 0 element. And then we have only one element on the right. So we have 4, and we have the 3 and 4 as the result of this node. And then we have the G. We want to combine the L and G. So we have 1, and then we have 3 and 4, and we combine it with the pivot that we used before. So in this case, the pivot is the E. So L, and then combine with E, and then G. After we finish with the left one, we will go to the right. We have 7, 9, and 7. Okay, there are 2 7s. So we want to check the element which is lower than 7. Is there any element lower than 7? No. Then we have only 9. So 9 will be in the right, and we will do with the 7, 7, and 9. And at the end, we will join into a root So we will use the L, which is 1, 2, 3, 4, and then we will use E, and then we will use G. Okay. In the worst case of the quicksort, okay, the worst case of quicksort occurs when the pivot is unique minimum or unique maximum element. Let's say if you use 9, what happened? If you use 9 as the pivot, it means all the nodes will be on the left. No element on the right. So that is the meaning by the worst case of quicksort. One of L or G has the size n minus 1 and the other has size 0. Okay, so this is the worst case. And the running time is proportionally to the sum. So it will be n plus n minus 1 plus n minus 2 plus blah 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 until 1. And it means the worst case is, if we have this kind of sequence, it will be n multiplied by n minus 1 divided by 2. So it is the sequence, and then we know that this one is the n power of 2. The worst case will run at the on power of 2 for the quicksort. So the visualization is something like this one. Let's say if we select the pivot value, which is the minimum, the most minimum, then there will be no element in the left. There is no element in the left, but it will go on the right. It will go on the right. And the time will be n, and then minus 1, and so on. So the expected running time, it depends on how you can choose the pivot. Consider a recursive call of quicksort on a sequence size S. We call it a good call if the size of L and G are each less than 3 multiplied by S divided by 4. Okay, for example, this one, 1, 2, 3, 4, 5, 6, 7, 8. Okay, what does it mean by this? 3 multiplied by 8 divided by 4. So we have 24 divided by 4, 6. Okay. So if it is less than 6, yeah, we can say it is good call. But if it is greater than 3 multiplied by S divided by 4, then it is a bad call. So this one is 1, 2, 3, 4, 5, 6, 7. Okay, we have 7 elements. Actually, we need to have 6 based on the 3 multiplied by S divided by 4. Then this is bad call. A call is good with the probability half. What is the meaning by probability half? Half of the possible pivots cause good calls. So let's say if we have like this sequence, this part and this part, it will be bad pivots because this is the most minimum and this is the most maximum. So the good pivots will be in the middle. So we call this is the probability half, because let's say if we have 16 Okay, we have 16 numbers. Then 4 on the right, 4 on the left. Then it means there are about 8 elements, which is bad pivot. And there will be 8 elements, 8 possible elements, which are good pivots. Okay? That's why we call it, this is the probability of half. Yeah, this is how we can calculate, okay, if we want to expect the expected running time of the quicksort. If you are using the coin, okay, the probability of toasting coin is like 50%. So if you have the coin and then you want to get the number of k heads, okay, so it is from the probabilistics. Of course, yeah, the expected number will be 2k. So here, what I want to explain here, if we have like this tree, we have the expected head. The expected head is the same with the expected head on the merge sort. Okay? The expected head is the half. If it is half, then we have log n. If it is half, then it is log n. But if we choose the wrong pivot, it will be in the worst case. I divided by 2 ancestors are good calls. And the size of the input sequence for the current call is at most 3 divided by 4 power of I divided by 2n. Yeah, if you want to calculate this one. Okay. So what I want to say from here is, if we have a node of depth 2 log 4 divided by 2n, the expected input size is 1. So this is from the idea of this one, 3s divided by 4. Okay. And then if we have, if the condition fits with the good call, then the expected height of the quicksort tree is O log n. Okay. If it is in the good call, then the expected height will be log n. And we know that the amount of work done at the nodes of the same depth is On. So we will do n times. That's why the expected running time of quicksort is On log n. This is in the case of you choose the good pivot. There is another thing, they call it the in-place quicksort. We can implement the in-place quicksort. Okay. So by doing the partition, we use replace operation to rearrange the elements of the input sequence. So for example, we first, the element less than the pivot have rank less than H. So we have rank L and R. If the element L is greater than R, then finish. I is a random integer between L and R. And then X is the element at rank I. And then we will make a partition. The partition will be 2, which is H and K. And we will do the recursion. The recursion will be in place quicksort based on the L, H minus 1. And after we finish with this, we will do the in place quicksort K plus 1, comma R. So the idea is just make it the low and the higher rank. So this element less than the pivot have rank less than its, and the elements equal to the pivot have rank between its and k, and the elements greater than the pivot have rank greater than k. And we have the recursive call. We consider the elements with rank less than its, and we have the elements with rank greater than k. So the way to do this partitioning is this is the in place. Okay. We can perform the partition using two indices to split S into L and E and G. So L is low, E means equal, and G means greater. So you can split S into L and the combination of E and G, or you can split, if you want to split E union G into E and G, that's also fine. And we can make something like this one. I have this number, and then I have the J starting position here, and then K, which is the last index. We will repeat until J and K cross. Okay. So J will increase, and then K will decrease. Scan J to the right until finding an element that is greater than X. So X is the pivot. So first we scan. This is greater than 6. No. This is greater than 6. No. Greater than 6. No. Greater than 6. No. Greater than 6. No. Greater than 6. Yes. Okay. And then we can do the next. Scan K to the left until finding an element which is less than X. X is the pivot. This is less than 6. No. 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 Less than 6. Yes. Then we swap. We swap elements at index J and K. And then after this, again, we will select another pivot. So this will be repeated until J and K cross. So if J is here and K is here, then it is cross. So if it is cross, then you will select another pivot. So this is the example from the book. Okay. I have the L, I have the R here. And then if I have the, let X is the 50. Okay. X is 50 is the pivot. So I want to check, is L is higher than 50? Yes. Okay. And then we will check from R. Is R is less than 50? No. Then we will go to next, 31. 31 is less than 50? Yes. Then we swap. After we swap, so we still use 50. We put this as L. This is greater than 50? No. This is greater than 50? Yes. And then check. This is less than 50? Yes. Then swap. And next, after we have this L and R, we swap. And then we have 45. 45, it is L and R in the same position. So we will do next. R is now in cross with the L. Okay. So before with this one, we will check 50 is less than 60, sorry. 45 is less than 50. Yes. And 63 is greater than 50. Yes. So we swap. And yeah, this is the first. And then we will select another pivot to, because this is still not in the sort, so we will choose another pivot to make the sequence again. This is the in-place quicksort. So that's why there are many ways to do the sorting. Okay. And this idea is based on the quicksort. And this is the code. It will go until the, yeah, we will check the left, we will check the right. And then until left is greater than the right. If it is not, then we will do the loop. If in the case of we have the left and the right, okay, so every time we will, if we finish until the step after we swap all of them, we will do again the in-place quicksort by using the A and left -1. And then if we finish with this one, we will do the in-place quicksort with the left +1 until the B. Yeah, based on this performance analysis, okay, we can check which one is the best one. So at the final presentation, I hope that you can also show this kind of algorithm analysis. Okay. Quicksort, okay, it is n log n expected. Okay. Why it is expected? Yeah, if you choose the good call, then our expectation will be n log n. The heap sort, I don't explain it, but yeah, based on the authors, if you want to check, it is n log n. Merge sort, it is n log n. So if it is n log n, of course, it is good for large input. If it is n power of 2, yeah, it is slow, or it is good for small input. Okay. The last part that I want to explain is the code. This is the code of the binary research tree. And I give one code about the sorting comparison. So I give you this code. You can have some idea when you are trying to do the experiment for your team project. First, we will plot the time. You know how to do this time performance. Okay? We will check the starting time and then the ending time. And then we want to get the elapsed time when we call the algorithm. Okay. So this is the code of the merge sort. This is the merge sort based on the code that authors share. We have the merge, and then yeah, we have the this is the merge function. This is the merge sort. The merge sort is the recursion. The merge sort is the recursion. After we finish the recursion, and then we will merge the element S1 and S2 into the S. I would like to put the test into a list. Let's say I want to make one list like this one. So I want to see if I want to run it with the merge sort. Okay, so the runtime means I would like to call this one. And then fn is the function that I'm going to run. And s is the data. So this is the function. The function is the merge sort. And then s is the sequence that I want to use. After I have the time of this small data s, I will put it into the test time. The test time is a list. So the first experiment will be saved in the first element. Yeah, I'm just giving you an idea. Let's say you have your data, okay, and then you want to generate your own data, and this is one idea. I want to see if this data, how can I generate a new data with bigger one? Okay, I can try to find the expected mean. The mean of this data is about 6.8 and the standard deviation is about 3.7. Then I can have this number A1. Okay, A1 is the time because it's only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it's only 11 data. Very fast. That's why it's 0. Now I'm going to make a new list as 10. Okay. Let's say I want to generate a random number. So this is a random number based on the random Gaussian values. In the random Gaussian values, it is based on the like normal distribution. We need to consider the mean and the standard deviation. So if you already have the mean, which is 6.8 from this one, and then if you have the standard deviation 3.76 like this one, so I can generate a value randomly. And then I want to generate 10 numbers. So before this one, I make a seed. So the seed, it means my computer and your computer. If we run this random generator, it will give you the same random number if you use the same seed number. If you use different seed number, of course it will be random, totally random. But if you use seed 1 and if your computer use seed 1, the random number will be the same. So we have the Gaussian 6.8 and 3.76. Okay. Okay, we have this one. Now, I want to generate more data. I have 100 data. Now I want to generate more data. I have 1,000 data. Now I want to generate more data. I have 10,000 data. So I can run for every those data with the time performance function. Let's say A100, A1000, and A10,000. Now I would like to make the data with this X 10, 100, 1000, and 10,000. So the test time, okay, this is the test time. And you can make the plot. So this is the plot. Because I'm doing with the merge sort, okay, this is the plot for the merge sort. I'm using the X, which is this 10, 100, 1000, and 10,000. And we want to plot the test time. Now let's suppose I have this quicksort. Okay. So I also took it from the author. Okay, I have this Quicksort, and then I will run again. This is the runtime of the Quicksort with the number of data 10, and then this is the Quicksort with the number of 100, 1000, and 10,000. And again, I will make a plot. Okay, based on this plot, okay, it seems that the Quicksort is a little bit higher compared to the merge sort. Actually, you need to run this one several times. Okay, you cannot run in one time. It depends on your computer performance. Sometimes when you run one time, if your computer also run another program, it may stuck sometimes. So for example, if I run again, yeah, the result is slightly higher. So it depends how you run your algorithm and what is the condition of your computer when you run your algorithm. You can check the best one, okay, to show this kind of result. And suppose I have another algorithm which is bubble sort. So I took this one from internet. Let's say I'm using this one, and then I again run with the data 10, 100, 1000, and 10,000. And then I would like to apply this. Okay, so you can see the bubble sort is the slowest one compared to the other algorithm. So in the final presentation, I would like to see this kind of graph. When you run your algorithms, at the end, you need to show the time performance. If you use 3 algorithms, then you can show those 3 algorithms. If you use 4 algorithms, then you need to show 4 algorithms. Okay? It depends on how many algorithms you use. Okay, I think that's all what I can explain. Is there any question?